All right. Good morning, everyone. Welcome back. Per usual, just a few dates on the quote whiteboard here. 2.1 and 2.2 are due today. Remember, you got a little bit more time with 2.1. That's why they have coincidental due dates. And then 2.3 and 2.4 are so far out because, well, we have spring break next week. We won't be meeting. So enjoy your time off. Hopefully, you can use it productively, while simultaneously having some fun. But with that being said, we're going to pick up where we left off with 2.4.
We are going to pick up where we left off in 2.4. Last time we had done the first example, so we're going to do the second example and then get into some other stuff. But as a quick reminder, this section for now, so far, what we focused on is the idea of parallel versus perpendicular lines, which we hope you've seen as a concept before, that parallel lines never intersect. The black lines are the parallel, the blue little step-looking things were me just representing the slopes on them and saying they were the same. And then perpendicular lines, we said instead of not intersecting, they intersect at a specific angle, 90 degrees. So they form a right angle, a nice corner. Then we said that based on these two lines, based on some math, the first one's pretty obvious, the slopes have to be the same. Parallel lines, slopes have to be the same. But for perpendicular lines, they have to be what we call negative reciprocals, which means you change the sign and you flip it. You change the sign and you flip it. Not just flip it, you change the sign and flip it. We have talked about all the different forms of equations of lines. We've talked about the point slope form, the y minus y1 equals m times x minus x1. That's where we generally start, which I said it out loud there, but here's the typed up version. That's the point slope form. We call it point slope form because in it you can see a point, the x1 and y1, and the slope m. But we said most of the time we want to solve these for y to put them in slope intercept form because it gives us consistency. And when it solves for y, when you solve for y, it's mx plus b, slope intercept form. Why do we call it slope intercept form? Because you got a slope and then a n-intercept, specifically the y-intercept, always 0, comma b, where b is that number there with its sign. Okay, so we did example 1, where instead of me giving you a point and a slope, or 2 points, I gave you a point and an equation of another line, and that other line was parallel. So parallel means that the slopes would match. So the first thing we had to do was find the slope of that line, which was 5. Say our new line will have the same identical slope, and then just use that slope and the point we were given in point slope form. We said that once you have the slope, you don't need the first line anymore as long as all you have to do is write line 2. Now, if they ask you to graph line 1, that of course means you still need it. But you don't want to like permanently cross stuff out. I'm just saying that, hey, cover that up for a second because you don't want to accidentally use it. Example 2, we'll see a lot of similar things, but in this example, instead of the line being parallel, it's going to be perpendicular. So that's going to change one aspect. So write the equation of a line going through the point -2, comma 3. So that's our x1 and our y1. And then perpendicular to y equals 4x minus 50, 20. So this is our first line. And if it's not solved for y, then you'd have to solve it for y so that you could see its slope. But that's already done for us. So the number in front of the x is slope. So m1 is going to be 4. The slope of the first line, the line that I'm not going to mess with anymore after this, is 4. So what that means is line 2 has a slope, what we call m2, so that we can tell we're talking about the second line. Well, that's perpendicular, so it's the negative reciprocal, which means we flip it and we change the sign. So that 4, we could rewrite as 4 over 1, and then when you flip it and change the sign, you don't just get 1/4, it's -1/4. So those are the perpendicular slopes. 4 versus -1/4, those would be perpendicular lines that would meet at a right angle. So once we have that, all we need is the slope of the line we're supposed to create, along with the point it's supposed to go through. We don't need this y equals 4x minus 50, 20 anymore. Now again, I might, or your homework or a test might ask you to graph that as well, in which case, don't black it out permanently. I'm just saying, hey, don't look at that. Pretend it's not there. All we need is the 2 things that I have highlighted. All right, so we go y minus y1, so y minus, let me go back to black. There we go. Y minus y1, which would be the 3, equals the m, not this m, not that one, that's the slope of the first line. We need to use this one, the perpendicular line, which is negative 1/4, parentheses, and then x minus x1, which is this negative 2. That'll be a double negative, so you got to do those parentheses like that. And then just take this and solve it for y. So let's change that to an x plus 2. So that's y minus 3 equals negative 1/4, parentheses, x plus 2. We need to distribute the negative 1/4, and you have got to remember how to multiply fractions. There are no excuses for not knowing how to add, subtract, multiply, and divide fractions in a pre-calculus course. If you don't remember how to do that, go and do 100 of them, do 1,000 of them. You know I say this stuff over and over and over. So that's y minus 3 equals negative 1/4 times x is negative 1/4 x. Nothing really to think about. When you do the negative 1/4 times the 2 and the 4 are going to reduce. The 2 will reduce to a 1, and the 4 will reduce to a 2. But again, that's for the second piece, the part without the x. Now the minus is still going to be there, so that becomes minus 1/2. Again, if you need to see that to the side, that's the negative 1/4 times the 2, which 2 goes into 4 twice and into 2 once, which is why we get negative 1/2. Then, to finish this up, we just got to move the 3 over, so we add 3. Oh, look at that, we're adding and subtracting fractions. We get y equals negative 1/4 x, and then 3 minus 1/2 is going to be a plus 5/2. Where did I get that from? Negative 1/2 plus 3, which you can write as 3 over 1, which is negative, the LCD would be 2. So negative something over 2 plus something over 2. 2 goes into 2 once. 1 times 1 is 1, so that's still negative 1/2. And 1 goes into 2 twice. 2 times 3 is 6. And then negative 1 plus 6 is positive 5. Again, absolutely zero excuse to not be able to do this in a pre-calculus setting. You never get to forget how to handle your fractions. And we have our answer here. That is in slope intercept form. The first one, the first bit of black ink, that was point slope form, not PD, excuse me. It's just bad handwriting, point slope form. Point slope, point slope. Slope intercept, slope, and then the B value of the intercept. You could even, if you really wanted to now, say that B is 5/2, so your y-intercept is 0,5/2. That's something that may be an important aspect to understand for the problem, or it may be a question for the problem. This is probably one of the more challenging problems because of the perpendicular aspect. This is the one that students mess up more than anything else. The second thing students mess up is they want to use this 50/20 somehow. It's completely irrelevant for the problem. Same as how I mentioned that 800 was completely irrelevant for example 1 for creating the second line, because it's only based off a slope. Example 3, and I actually have the solution kind of typed up there, so let me hide that for a second. Last one for this type of problem, and then we're going to move on to something slightly different. The ... is just meaning same instructions. Write the equation of a line going through the point 5, 8, so that's our x1 and our y1, and perpendicular to x equals 11. So I didn't actually give you the slope. I did not give you the slope directly, but I did give it to you implicitly. So we got to be perpendicular, which means we're supposed to find the slope and do the negative reciprocal of it. Well, this one's going to be a little weird because of the fact that this does not have both variables. This only has one of the variables, which means it's one of the special cases. When you only have y equals or x equals, it's one of the special cases. To remind us, horizontal lines are of the form y equals a number. Vertical lines are of the form x equals a number. Me being a broken record, you never get to forget this ever again. It's very easy to swap the x and the y, flipping a coin in your head. Don't do it that way. You've got to know that horizontal is y equals and vertical is x equals. You've got to understand that the slope of a horizontal line is 0 and the slope of a vertical line is undefined. And I mentioned that in these examples. 0 for horizontal, undefined for vertical. Why am I bringing that stuff up again? Okay. Well, perpendicular to x equals 11, so I didn't tell you the slope, but this x equals 11, this line 1, as I'm going to call it, has a slope of undefined. And we're supposed to make a perpendicular line, which means we're supposed to take the negative reciprocal of that. Now, some of you may understand that undefined means it's anything divided by 0. So when you flip anything divided by 0, it's 0 divided by anything. And even with the negative in front, that's 0, which tells you the slope is 0, which tells you you're making a horizontal line. But a lot of people get confused with that, so I like to think of it a little more geometrically. So that's what this says. X equals 11 is vertical. Because we need to make a perpendicular line, we're going to need to form a horizontal line. So again, because our original line is vertical, and we need a perpendicular line, here's a vertical line. The only way to make a perpendicular line and a vertical line is a horizontal. So this would be line 1, this would be line 2. These are not x and y axes, I'm just saying these are the lines somewhere in space and time. So because x equals 11 is vertical, we need a horizontal line because of its perpendicular aspect. Horizontal lines are of the form y equals a number. So whatever we're going to end up writing, it's going to be y equals 7, y equals 13, y equals negative a million, y equals 40, whatever it might be. That's it. There's not going to be any x's because horizontal lines are of the form y equals a number. And the number tells you how far high it's going to be. So what you can actually do is graph the point, and that's where your horizontal line should be. So these will be our x and y axes. This point is 5, 8, so that's right. 1, 2, 3, 4, 5, up. 1, 2, 3, 4, 5, 6, 7, 8. So we're supposed to make a horizontal line. Again, this was vertical, so we make horizontal, and it's got to go to this point. So this is our line. I actually prefer to graph this line even though I didn't ask for it, because now I can look at this and say, oh, well, it's very obvious. This line is y equals 8. Why? Because that height's 8. So the height is constantly 8. So that's what the rest of this says. So the y coordinate of the given point must be in the number in the equation. Now, I didn't say that here, but that is the fact that you could learn ultimately. Because this was an 8, this is an 8. If this right here had been a 20, this would be a 20. If for some reason our answer needed to be of the form x equals, maybe we were doing a parallel line instead of a perpendicular line, then we'd be making a line that looked like this going through the point, which would tell us it would have to be x equals, and it would be 5. Now again, that's if I asked for a parallel line to x equals 11. I didn't ask for that though. I'm just giving you extra information, an extra problem, if you will. All right, so again, example 3 is kind of a special case because it's generally better to think about this geometrically than algebraically, but you have to understand that special cases mean you have to think special ways. How did I know this was a special case? Because a variable was missing in the line. Variable's missing, special case. There we go. All right. Slope as a rate of change for functions. So when you go into calculus, you're going to study something known as change over and over and over and over and over. Now we're already starting the study of change, believe it or not. With slope, slope is a rate of change. A rate just means fraction. The word rate means fraction. Change means subtractions or differences. So what this says is slope is a fraction of changes. It's a y2 minus y1, that's a change, over x2 minus x1, that's a change. So the top is a change, the bottom is a change. The fact that we have two things on top of each other makes it a ratio, also known as a rate. Rates are ratios, are fractions, are divisions. They're all the same thing. Different names, same package. So this is a rate of change. This is known as a rate of change. This is known as a rate of change. It's a fraction of subtractions. It's the rise over the run. But now we're going to start talking about this for functions. This was just the slope of a line, which for lines, slope is boring. It's always the same. It's always 3, or it's always -5/2, or it's always 0. It's always undefined, whatever it might be for one particular equation. But we are going to open ourselves up to the wonderful world of functions, not just lines. So quadratics, cubics, quartics, general polynomials, rationals, exponentials, square root equations if we wanted to. So that's what we mean by functions. We're not just going to be talking about lines anymore. Now, we're still going to be dealing with straight up equations, equations that are functions. But again, when we say functions here, we just mean crazier equations, not just y equals 3x plus 2, maybe y equals 3x squared minus 5x plus 7, or y equals x cubed plus 20x minus 3/2. I don't know, it can be anything. Y equals the square root of x and then minus 17. But here's the thing, when we're talking about lines, once again, that's a constant slope. When we're talking about curves, things that look like this, see the slope here, if I want to talk about the slope at this point, that line would determine the slope, the rise and the run. If I want to talk about the slope at this point, it's the exact same thing. It's the same rise and run. But if I want to talk about the slope, say at this point right here, at that little peak, that little relative extrema, that slope would be 0. If I want to talk about the slope at this point, that slope is probably something like 3. If I want to talk about the slope at this point, that slope is probably something like -1/2 maybe. The slopes are different. So what do? To find a slope, we need 2 points. Well, we're not going to find the slope at a singular point in pre-calculus. This right here is a calculus concept, but we're in pre-calculus, which means we're doing the stuff right before it. So what we're going to introduce is what we call the average rate of change. The average rate of change. So instead of just looking at one point, I'm going to draw this up one last time, but a little bigger this time. Let's say we have our curve. And we've got some point 1 here. So this is the first point, and our second point is here. We're going to be doing what we call a secant line, where we connect those 2 points, and then finding the slope of that. We will find the average rate of change equals the slope. So the average change between these 2 points would be the slope of that secant line. The average rate of change, AROC, average rate of change, is the slope of that secant line. So we're not saying the slope at this point is whatever that is. Let's say this slope was -1. I'm not saying the slope here is -1. I'm not saying the slope here is -1. I'm saying that if you manage to do calculus and find the slope of every single point in between them, and including those two, that the average slope, the average steepness, would be -1, the slope of that line. Now, if I drew it somewhere else, let's say I did a blue one, let's say we did point 1 here and point 2 here, and then we have a secant line, the average rate of change would be the slope of that line. But that would be the average rate of change of these 2 points, which would be completely independent of the average rate of change or slope of these 2 points. Because this red one is a negative slope, this blue one is a positive slope. So again, this illustrates the changing slopes. So I'm going to go ahead and spoil what you do in calculus because you've already seen the formula. It was that f of x plus h minus f of x over h. What that does is it takes the average rate of change formula, but it merges these 2 points into one via calculus. And it sounds like a crazier idea than it actually is. The formulas you ultimately get are quite simple for a lot of them, but you have to learn about it in the process. All right, so getting it down to what we're actually doing, skipping that little calculus thing. So slope is a rate of change, as we talked about, and the average rate of change formula for a function at 2 different x values is, so we're going to go AROC for average rate of change. It's going to be f of x2 minus f of x1 divided by x2 minus x1. This is literally the slope formula. 3 exclamation marks. This is not a new formula. It is just the slope formula, y2 minus y1 over x2 minus x1, but put into function notation. So again, this thing right here is basically y2, excuse me. This right here is basically y1, y2 minus y1 over x2 minus x1. I've already said you never get to forget the slope formula. And here's one of the many reasons why. First of all, we're going to make it a crazier looking formula. Well, Mr. Beckner, why would you ever take that simpler looking formula and throw function notation in it? Well, because first of all, now we know these things are functions, not just random equations. Second of all, this is how calculus is done. We generally deal with things in function notation, so we've got to get used to it. Third, and the most important step is, when you had m equals y2 minus y1 over x2 minus x1 before, B4, I'm just saying, abbreviating before. Not saying problem B4, that's not what I'm referring to, the word B4. I had to give you the x1 and the y1 or the x2 and the y2, or I at least have to give you an equation and the x values, which is usually not done. When we give it to you this way, the only thing I'm going to give you is the x values, and you have to find the y values by plugging the x values in. Once again, this right here is just y2. This right here is just y1. It's just written in fancier lingo. But the lingo has its strengths, as we've discussed. So again, this will feel like there's one new step in that you'll have to find the y values. So first you'll have to find the respective y values by plugging the x's into the function, then use the formula, which above, it's not on the board. There is no board. So the first thing you do is find the respective y values. How do you find y values? Very simple. You plug in the x values and you evaluate it. So that gives you your point, your x1 and y1, but you're calling it x1 and f of x1. Or then when you plug in x2, you get f of x2. So again, this is just y2 and y1, just written in a different language. So you plug in your x values to find your y values, you plug them in and you find a slope, and that's literally it. There's nothing complicated about this. You do have to memorize this formula just like you have to memorize the slope formula, but again, this is literally the slope formula. It's not any new memorization as long as you understand conceptually that y is the same as f of x. It's really nice, in fact. All right, so let's try this out finally. And let's not show everything all at once. These should have little subnotation. So this is f of x is x squared plus 5x minus 10. This is x little 1 equals 0, and x little 2 equals 4. Word is just very much a pain in the butt with the sub and exponent notation sometimes. So we're going to find the average rate of change. Again, what this is symbolic of is finding the slope of a secant line if you were to connect wherever the x1 and the x2 are. In this particular problem, the 0 and the 4. All right, so the first thing you do is find the respective y values. I only gave you x values. I did not give you y values. I generally won't give you y values. Nobody will, generally speaking. So again, the first thing you got to do is find f of x1, which is f of 0, because 0 is your x1. You're just plugging that into the function. So that's 0 squared plus 5 times 0 minus 10, which is 0 plus 0 minus 10, which is negative 10. So that says f of 0 is equal to 10. If you prefer writing this as points, you can write the coordinate 0, 10. Both of these are accurate information. It sounded weird. I don't think I said it wrong, it just sounds weird. Both of those bits are accurate pieces of information. That makes it sound a little better. So that was your x1 and your y1, so to say. Now let's do the f of 4, that's our x2. So that would be 4 squared plus 5 times 4 minus 10, which is 16 plus 20 minus 10. 16 plus 20 is 36. 36 minus 10 is 26. So that says f of 4 is equal to 26, or if you prefer it as a coordinate pair, it's 4 comma 26, which would be your x2 and your y2. And now all we're doing is literally the slope formula. Whether you wrote things in function notation or if you wrote them as coordinate pairs, your average rate of change, a rock, from 0 to 4 specifically, and if you wanted to write that, you can, but it's implied here, would be the f of x2 minus the f of x1. Let me show that formula one last time. It's this. F of x2 minus f of x1, which were the y values that we found, the 26 and the 10, divided by the difference of the x values. So the f of x2 is this. It's the 26. That's the y2. Minus f of x1 is that, the 10. Again, also known as y2 minus y1, over the x2 minus x1. The x2 was 4, and the x1 was 0. Make sure you're consistent. Put the seconds minus the first, or the first minus the seconds. As long as you're consistent, it won't matter. 26 minus 10 is 16. 4 minus 0 is 4. 16 divided by 4 is 4. That says the average slope from x equals 0 to x equals 4 is 4. One second, I meant to have this open already. I forgot, but that's fine. It takes a second to open. Boom. So here's something I'm going to do real quick. I'm going to graph this x squared plus 5x minus 10. I'm not asking you to know how to do that yet. It's pretty easy to put in technology. That's a plus 5x, not a minus 5x. Plus 5x minus 10. Now, I can't really see all these points. The 0, comma, negative 10. I wrote something wrong, didn't I? Unbelievable. Okay, so the answer is not 4. I've got to go back and correct some things. F of 0 was negative 10. I dropped the negative there. That was a boo-boo. So I got to go back and just make a couple corrections. I'm going to do them with black so you can see it. The f of 0 is negative 10, which says that should have been 26 minus negative 10. I'll put it in red here for the change. So again, that should be 26 minus negative 10, not 26 minus 10. I'm sorry about that. I'm glad I caught us though. All right, so that's 26 plus 10, which is really 36. That's what that should be. And 36 divided by 4 is 9. So the average slope is 9 from x equals 0 to 4. Again, I'm sorry for that. I lose a couple points for that on my test. So again, f of 0 was negative 10. I dropped the negative on accident, so I made a mistake. If I had put this in a test, it would have marked it wrong. And then I would have figured out, oh, nope, I made that boo-boo. But how did I know I made that boo-boo when I pulled my graphing calculator out? I saw this thing was way down here, and it's like, wait a minute, that's negative 10, not positive 10. I must have made a mistake. Yep, I forgot to bring my negative over. Okay, so this window isn't really good because 0, negative 10, you can just barely see. You definitely can't see the 4, comma 26. That's way up here because that's a height of 10. So I'm just going to change my window, the y minimum to like a negative 15, and the y maximum to a 20. This is not something, I'm sorry, not 20, 30. This is not something you need to know for this class, so I'm not going to spend hours teaching it. But here's a good picture of the graph. So here we've got that point. There's our 0, comma negative 10. And then the 4, 26, right, 1, 2, 3, 4 is about right here, roughly. So there's our 4, 26. So the slope at this point is probably something like 7. The slope at this point is going to be a much bigger value. We're at 8, 13, not much bigger, but bigger, 13. And then the average slope between those two, if you were able to manually calculate every single slope at every individual point, which is extremely tedious and no one ever actually does, you'd get 9. What I'm saying is if you formed a secant line, which means go between both of them, and I'm not going to dot it because of the thing I'm using, so there's my secant line, the slope of that line is 9. So you'd go right 1 up 9, right 1 up 9, right 1 up 9, right 1 up 9, and you could actually connect both of those points by doing that 4 times. So if I were to do this with different points, if I said, I want to do this now with x1 being, I don't know, negative, whatever that value is, and then this value is. If I use those as my x values, this would be my secant line, and we can see that that slope would be 0. But again, that's a completely different problem. I'm not doing that problem. I'm just saying that the slope highly depends on the x values you use. The x values determine the y values, and those in pairs determine the average slope between the 2 points. There's even a theorem that says the average slope between the 2 points has to be the slope at least 1 point between them, but that's calculus that we're not going to do. All right, so there we go. Now, let's not make any more mistakes. I get 1 a day at most. B, f of x equals x plus 3 over x minus 5. Now, that slash with the parentheses might throw you off a little. This is what it should look like more traditionally, with them just on top of each other, but that is the same thing. And this says our x sub 1 is 2, and our x sub 2 is 10. So those are the x values that will determine the average slope. The average slope will be different if you went between 0 and 5, or -2 and +2, or 0 and 1, or 0 and 10, or 0 and 50. We specifically want the change between 2 and 10. So first we got to find the f of x1 and f of x2. So we plug these in. F of 2 would be 2 plus 3 over 2 minus 5, which is 5 over -3, which I don't like negatives and bottoms, so that's -5/3. So that point is f of 2 equals -5/3, or 2 comma -5/3, whichever way you prefer to write it. So there's the x1 and the y1, or the x1 and the f of x1. Now let's do f of 10, which would be 10 plus 2 over 10 minus 5, which is 12 over 5. And yes, that's 2 2/5, or yes, that's 2.4, but let's leave these as fractions. So that says f of 10, and not mixed number fractions, because they're a pain in the butt to do arithmetic usually. So f of 10 is 12/5, or as a point, that's 10 comma 12/5. 12/5, 13/5, 13/5. I knew I was making another mistake. 3, 13, 13, 13, 13. X plus 3, not plus 2. 10 plus 3 is 13. 13, 13. So the x1 is the 10 as prescribed. The x2 is 13/5. All those 2's threw me off, and I wrote 2 again. So I almost made 2 mistakes, but I caught it. So now we just do our slope formula, the average rate of change, the slope of the secant line between these 2 points. y2 minus y1, aka f of x2 minus f of x1. You're going to not like me for a bit. This is 13 over 5 minus -5/3. You're not going to like me because of the double negative and the fraction inside of another fraction. And then that's over x2 minus x1. X2 minus x1 is 10 minus 2. That was x2, y2. Kind of looked like I wrote an x the first time. Okay, well, you can combine the tops by getting an LCD, so I'm just going to focus on this section. I'm not going to focus on the 10 minus 2 bit for a little. I'm just going to focus on the top. So the LCD in the top between 5 and 3 would be 15. So we're going to change those to 15s. I'm leaving the 10 minus 2 for now. We're going to make these 15s. That's a 15, that's a 15. The minus a negative makes a plus. You better know how to get common fractions. 5 goes into 15 3 times. 3 times 13 is going to be 39. Then for the second one, 3 goes into 15 5 times. 5 times 5 is 25. And then 39 plus 25 is the same as 40 plus 24, which is 64. So that's 64 over 15 in the top. Then here's our big fraction bar. The 10 minus 2 is obviously an 8. But it's usually not a good idea to leave a fraction divided by a whole number. So let's write that 8 over 1. Because now this is just division of fractions. A fraction divided by another fraction. Let's write it that way, the old school way, with the division symbol. That way we can then change the division to multiplication and flip the 8 over 1. That's what we're going to change next. So this average rate of change becomes 64 over 15, I'll use color to show the change, times 1 over 8. And the 8 and the 64 can reduce. 8 will go into 8 once, and into 64 8 times, giving us an answer of 8/15. That is the average slope between those two lines. Again, I know this is a little more of a pain because of the fraction math, but you are expected to be able to handle fraction math. Hold on, give me 30 seconds. Okay, didn't need 30. All right, so that was B. So again, if you wanted to kind of visualize this, and again, this is not part of what you have to do, I'm just showing you ways you can kind of visually see things. Let's go back to our calculator, the y equals screen. That equation was x plus 3 over x minus 5. I have to put it in parentheses like you originally saw. It's also the reason I wrote it that way originally, so you understand. I really might not need as much space this time. So let's see. The 2 comma negative 5/3, that's right 2 down 5/3. That was right here. That's the first point. The 10 comma 13/5, that's right 10, and then up 13/5, which is about there. No, that's not right. That's not right. Hold on. Undo. Am I in, let me put myself in the standard window first. It's throwing me off. No, zoom 6. There we go. There we go. Okay. So the 2 comma negative 5/3, right 2 was here. And then the 10 comma 13/5, it's right 10, and then 13/5 is here. There we go. So that slope right here, if you connect these dots with a secant line, again, which you would traditionally dot, but we're not worried about it. The slope of that line would be 8/15. So you can see it's positive. It's not too large. So I think that makes sense. Now, none of the slopes on this side of it at any particular point is going to be 8/15. They're all negative. And then these are all going to be negative as well. So what's really weird about this one is because of the discontinuity, this asymptote that we'll discuss in chapter 3, something extremely weird happens with the average one, but we don't have to worry about that in deep detail, thankfully. All right, uno más. C, so this is f of x equals x cubed and then plus 1, with x1 being -2. I didn't write the little 1s and 2s because you don't have to technically, as long as you understand. And the x2 is 2. I could swap what I'm calling 1 and 2, it doesn't matter. So the first thing we got to do is find f of -1. I'm sorry, f of x1, which was f of -2. So that'll be -2 to the 3rd power plus 1, which is -8 plus 1, which is -7. So that says f of -2 is -7, or the point is -2 comma -7, whichever way you like it. Then we do f of +2, which would be 2 cubed plus 1, which is 8 plus 1, which is 9. So that says f of +2 is equal to 9, or as a point, that's 2 comma 9, whichever way you like it. So our average rate of change will be the f of x2 minus the f of x1 over the x2 minus the x1. So that's the 9, that's the f of x2, f of the second point, the output of the second point, minus the output of the first point, which was the -7, double negative. I'll check my numbers, make sure I'm not making any simple mistakes, right? Then over x2 minus x1, the x2 was the 2, the x1 was the -2. 2 minus -2, which is 9 plus 7 over 2 plus 2, which is 16 over 4, which is 4. And that's what actually threw me off, that I didn't catch my mistake earlier, because I knew one of these answers was 4, and I saw the 4 and just, I was like, oh, I'm good. It was x1 and x2 were stated in the problem. There's your x value, there's another x value, so implicitly that's the first one and the second one. So no, you didn't have to determine them, you just have to understand that even if they don't put the little subnotations, it still means the same thing. Cool, 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 cool. All right. I think that's it for the section. Should be. Yes, it is. All right, so that average rate of change, that's a great formula. Again, it is literally the slope formula, just in function notation instead of equation notation, y2 minus y1 over x2 minus x1. Literally the same thing. It's just we usually have to find the y values by plugging in the x values. But the strength of it as function notation is it allows us to plug in things that aren't just numbers, things like x and x plus h, and then that's what turns it into that difference quotient formula. You end up with f of x plus h minus f of x just over h after you do a simple little bit of arithmetic. And then you slap an extra little detail on it and you call it a calculus problem. So between doing this as well as the, that difference quotient previously, the name was escaping me for a second even though I literally just said it, that's calculus. All you do is one teeny tiny extra step and you're calculus students. What I always tell people, and I'm sure I've told you this at least 3 or 4 or 5 times, calculus isn't hard because of calculus. Calculus is hard because you have to remember all the algebra you've learned up to calculus. Maybe some trig too, depending on the type of calculus class you go in. All right, so that is 2.4. We have finished that section, which means the homework is this. Transformation of functions. When I say see board, I mean this is our board. 2.5, transformations of functions. This is a concept that we're going to see pop up again in chapter 3. We're going to see it pop up again in chapter 4. You're going to see it pop up in trigonometry if you go on to take pre-calc 2. Then when you go to calculus, whether you have the trig version or the non-trig version, you'll see this happen again. You don't get to forget it. So the 2 things you don't get to forget are the 4 or 5 or 6 basic graphs you're going to have to memorize, which I'm about to lay out for you, as well as how you can just simply shift them left, right, up, and down, reflect them across one of the axes, things like that, because there's some subtle differences to some of the details, but let's get there when we get there. All right, some basic graphs to memorize. Now, some people will say that you need to memorize the basic y equals x line. So this right here would be the line y equals x. And I'm putting a little star next to this one because I'm going to say I don't actually suggest that you memorize the line y equals x just off the cuff. You should be able to graph any equation of a line no matter what, whether it's y equals x, y equals 5x, y equals x plus 3, y equals 5x plus 3, y equals negative 17/3 x minus 2 halves. If there's no exponentials, if there's no square roots, if there's no absolute values, you are absolutely expected to be able to handle the graph of any line. I wouldn't even do this with the method we're going to be learning in 2.5. I would just find 2 points and plot them, or use the first point and a slope to find a second point and plot them, like we did 2 sections ago in 2.3. So that's why I have an asterisk next to this one. I really don't think this should just be flat out memorized to try and transform it by moving it up 3 and right 2 or whatever. So that kind of odd man or woman out. The ones that I really suggest memorizing are, and I'm going to even write these in function notation. This is our standard parabola, f of x equals x squared. That's our standard parabola. This is at the origin where it starts, and then it just goes up on both sides. Now, again, if you're talking about increasing, decreasing, this thing is decreasing and then increasing because we're only considering ourselves moving right. It's got a domain of negative infinity to infinity. It's got a range of 0 to infinity. And some of these things will lay out. But yeah, this basic shape, it kind of looks like a U. Very important to memorize that shape. Next up, let me put that a little more left, will be the x cubed graph. So this one has a similar kind of shape, but it points down on the left, and it still points up on the right, but it's kind of squeezed in a little more. So this is f of x equals x cubed. Now, remember how we talked about even and odd functions previously and the reflections about axes? This first one, again, I'm ignoring, when I say first, I'm ignoring this. I don't really like using that at all for this section, but I'm just leaving it up there with the asterisks saying, don't really include it, but it is basic. This function happens to be even because it is a reflection about the y-axis. If I only drew the right side with really wet ink and then I folded along the y-axis, this side would pop up automatically. So it's an even function. This function over here is odd because it's a reflection across both axes. If I just took this right half, which I drew poorly, if I just took this right half and then I flipped it both times, if first I flipped it over here and then I flip it again, you end up with the bottom half, the bottom left half. So that's why it's odd. Remember, even functions you reflect about the y-axis, odd functions you reflect about both. Remember, you don't say something is an odd function by flipping it across the x-axis. Flipping something across the x-axis, if you just do this, let's say, oh, here's the original part, and then I'm going to flip it this way, it would fail the vertical line test miserably because every single line is going to go through 2 points. So again, that's why odd functions are not just a reflection about the x-axis, it's a reflection about both. P-A-R-A-B-O-L-A, parabola. There we go. And then this is just known as the cubic, C-U-B-I-C. All right, so next up, this one kind of looks like, and I forgot my axis names here. There we go. Make that a little more prominent of a Y. Next up, we're going to have the square root graph. And the square root graph is very interesting. So this is f of x equals the square root of x. The square root graph looks like you took the parabola and you just tilted it on its side. You rotated it 90 degrees, or you reflected it about some other particular line that I'm not going to say because that's implied in 2.8. We'll get there later. But it looks like we took this and again, just kind of rotated it 90 degrees this way. But then you'll say, well, Mr. Beckner, that doesn't seem exactly true, because if you took this thing and rotated it 90 degrees, this is what you would get. So why isn't this the square root of x? Well, because it fails the vertical line test. That's not where that goes. Miserably. Every single line goes through twice. It's not a function. So basically what somebody said is just, well, cut off the bottom side, ignore it, and there you go, you got a function. And it works really well because square roots, as we know, spit out positive values. They don't spit out negative. So it wouldn't even make sense to have this down here because we don't have principal negative square roots. I had to say that very specifically. There is some weird, funky business that we're not going to talk about at our level. So yeah, because then it's not a function, and everything that we deal with is pretty much a function. So that's the relationship between x squared and square root. They are highly related to each other, and when we get to section 2.8, we will study that relationship between them. So there's nothing drawn on the left side at all. There's nothing drawn on the bottom side at all. It's just this. Again, it's like you took one of the sides of a parabola and tilted it on its side. All right, next up, that's a really big x-axis. You don't need that much. We have our absolute value function, which looks like a v. The absolute value function and the x squared function have a ton in common with each other. If you look carefully, if I was a better artist, you would notice that the left side looks like a reflection of the right side. And it is. So this function is also even. Now finally, and admittedly, this is one I'm generally not throwing at students, but it is still good to know. Let's do better on that axis. Would be the cube root. The cube root of x. Now, for the same reason that the parabola relates to the square root by just kind of tilting on its side, the same thing happens with the x cubed and the cube root. It's like you took the x cubed and tilted on its side. There's something else teeny tiny going on with it as well, but don't focus on that too much. Now you might say, well, Mr. Beckner, the square root one, when you flipped it, you had to cut half of its arm off because it wasn't going to be a function. Well, guess what? That's not an issue here because any vertical line is only going to touch the function once. Once. So square roots and cube roots are drastically different because square roots only have the one leg, whereas cube roots, you get both of them. And that's, again, because you can't take square roots of negatives. You can't take a square root and spit out a negative. But you can take cube roots of negatives, and cube roots of negatives are, in fact, negatives. So that's why these are such drastically different graphs. This thing doesn't have that, it doesn't have that, it's just this. So again, I don't use that last one that often, but I do want to make sure you see it. So you should memorize the shapes of all of these. Now, we said that the f of x equals x cubed was odd. If you think about it, if you reflect this twice across the y then the x, you will see that this is also odd. The square root of x is neither. It doesn't even have anything in a reflected zone, whether above or below. So it's kind of the odd function out. Not literally the odd function, the odd one out. The screwball, the weird one, whatever you want to say. So you have got to memorize these shapes. You must memorize basic shapes. 4 exclamation marks. If you can't tell me what an absolute value of x looks like, you're going to have major problems. If you can't tell me what a square root looks like, you're going to have major problems. If you can't tell me what an x squared looks like, you're going to have major problems. Because in this section, our graphs, we're just going to take these basic shapes and move them up, down, left, and right, and maybe mirror them once or twice. We're not going to say, all right, well, let's plot 5, 6, 7, 8, 9 points and then graph that way. That's not what we're going to do. This first one is odd. If you took this section right here and reflected it left and then down, it's odd, but that's only if there's no other numbers in here. Not all lines are odd, which is why I don't really want to leave this written up here permanently. Yes, this graph is odd, but lines usually aren't odd. So that's why I didn't want to write it initially. So that was a good observation. Or a good question, I should say. All right, so memorize these basic shapes. If we were in a classroom, or if I had a functional camera, this is where you'd see me do the function dance, but you can just Google it and see someone, you take your arms, and it's kind of like doing the YMCA. You make the Y shape, and there's your X squared. Take one arm and point it down instead, there's your X cubed. Take one arm and do that on the side, but don't use your other arm, there's your square root of X. Take both arms and put it out really like a Y, nice and straight, there's your absolute value. You get the idea. That's the function dance. Try it out. If that helps you memorize it by being silly, do whatever works. I know silly always helps me. All right, so what are we going to do with these? Like I said, we're going to move these shapes left, right, up, down. Maybe left, maybe right, maybe up, maybe down, maybe left and up, maybe right and up. Just depends on the problem. And let's just deal with one concept at a time. First, let's deal with the concept of a vertical shift. So where we're just going to take these basic shapes and move them only up or only down. Now you're never going to move them up and down because that would be redundant. So what I'm saying here with this kind of lingo for a function with a known graph from before. So you might have something like f of x equals x squared plus 5001. Maybe this is what you're looking at. What I'm saying is this piece right here, the core of the function, you know what that looks like. Oh, x squared. I know that looks like that shape, but with a better pen instead of a highlighter. Then we would just say, oh, this 5001 is just going to move it up or down for reasons. So you have your core function, and then the number written to the side is just how far up or down you shift it. It's quite simple. So the c, I'm saying, is a constant, some number that you have to be given, like x squared plus 5001. So plus 5001 would say to take that parabola shape, this shape, that is, but move it up 5001 units. And then boom, you're done. It's more of a sketch than a super accurate graph, what we're going for right now. Conversely, if that had been x squared minus 5001, then we would shift that shape down 5001 units, and that would be going down very, very far. That's the basic idea there. It's just if you have your core function plus or minus a number, you're shifting it up or down, and the up or down is a direct translation. Plus is up, minus is down. It's pretty easy to remember. Spoilers, until we get to the horizontal where everything is different. We're not going to do that yet. Let's try out some examples. So example 1, sketch. Some people might say graph. I prefer the word sketch. And then you could have even more details by shifting, et cetera, et cetera, et cetera. But sketch means exactly what I just said. And for A, we're going to do f of x equals x squared plus 3. Let's make it a much smaller number. Instead of 5001, let's just go x squared plus 3. Much more nominal. So you go, okay, this has an x squared, so it's going to take that basic shape, that parabola shape, the nice, smooth U-looking shape, but where it goes up and left forever and up and right forever. But we're going to take that shape, instead of starting it right here, oops, instead of starting it right there, that particular height at the origin, you're going to move it up or down a certain value. How much do we move it up or down? Well, this plus 3 tells us to move it up 3. See, plus means up, minus means down. Oops, didn't mean to erase that far. There we go. So we just take our x squared graph. Now, if you want to draw ghost images, you can. I'm going to erase it for this one because it's pretty simple. So here is just your basic x squared. And then we just move it up 3 units. When you move that up 3 units, instead of sitting at a height of 0, it's going to be sitting at a height of not 1, not 2, but 3. So there is that point that used to be on the origin, and then you just make a parabola shape from that, sketching it by hand, and there you go. That's a little wider here than I really like. Let me do just a little better I wouldn't have counted that wrong on a handwritten test, but that looks a little better. That's it. That's the entire problem. There's nothing super complicated about any individual piece here, but what will make it feel complicated is once we start mixing in the horizontal shifts with the vertical shifts, because they are similarities, they are differences, as you could probably expect. So for B, let's go with f of x equals the square root of x minus 5. So again, the core here says this should look like a square root function, which means it should look something like this, where it starts originally at the origin, if your axes were there, and then just like a parabola on its side, but with only one of the legs. But we don't draw it starting at the origin because the minus 5 tells us that we have to shift it down 5. So we have our axes. So again, ghost image, this would have been the original x squared graph. And when we have a whole bunch of shifting and reflecting to do, I will leave ghost images so that we can see how things are actually working together. So I'm going to take that basic shape, but I'm going to shift it down 5 units. 1, 2, 3, 4, 5. So here's our minus 5. And now we just draw that shape starting there, something like this. And that's all it is. Again, one student might make it taller, one student might make it flatter. All of those are within an acceptable range of answers on a hand-drawn test or homework problem, but your homeworks and tests are generally in my math lab, so you need to understand how to do this by hand as well as by computer. So do the homework, otherwise the test might throw you off because the test question would flow like the homework questions. So those are our vertical shifts. At first glance, it doesn't seem like there's a lot to it. Ultimately, there isn't, but what we have to keep together ultimately is the organization. How do we tell a vertical shift from a horizontal shift? Because they're going to look similar, but they're also going to have contradictions to each other. All right. Horizontal shifts. So for a function with a known graph from before, so we know it's going to look like the x squared or the absolute value or the square root, whatever, the transformations of the following shift it left or right instead. Now, notice, let me kind of pull back for a second. I hope you can still read everything. Compare these, where the plus and minus c are, versus where the plus and minus c are here. The plus and the minus c here, when they were vertical shifts, those were outside the core, which what I'm calling the core, the function, the x squared or the square root. Whereas here, the plus and the minus c are inside the core. They're inside that actual function. So that's how we tell whether it shifts it left or right versus up or down. If this plus 3 had been in a parentheses with the x squared, if it had looked like this is what I'm saying, this would have been a horizontal change instead of vertical, because the plus 3 was outside, that says vertical. If the plus 3 is inside of the thing being squared, it's horizontal. Same thing here, this square, the x minus 5, that's outside of it. If it had looked like this, though, that would have been a horizontal change. That's how we can tell the difference between vertical and horizontal changes, whether they're inside or outside the core. And when I say core, I mean that basic square root or that basic absolute value or the basic square or whatever. So I don't want to leave that up there permanently. There we go. But here's the part that throws people for a loop even past that. All right, you got your outside versus inside concept. Inside is always left or right changes. Outside is always up or down changes. Notice something I just said, because that's going to be true even later. Inside the core is a left or right change. Outside is a vertical change. That is an amazing statement to have written down. I will write it eventually, but go ahead and write it down now. Trust me, even though I'm not writing it down. Remember, just because a teacher doesn't write something doesn't mean you shouldn't. My favorite parallel to that is I had a European history class in college. The teacher literally never wrote anything on the board, not one thing, but you better believe you were responsible for all the words that came out of her mouth. All right, so where's the last bit of weirdness? The plus C, well, plus before was up and minus was down, so you would think plus is right and minus is left, but it's not. Plus moves it left and minus moves it right. These feel reversed. This is the giant piece of organization that people can mess up on, because plus means left and minus means right, whereas before plus was up and minus was down. It was normal. Now it's backwards. So it's normal for vertical and backwards for horizontal. And there are reasons for this, reasons that we'll study maybe in calculus if we're together there. But it's a counterbalance in this format versus a direct effect in the other, because the way we actually write our equations and lines, we can do it differently. And let's just not get into that weird stuff. But that's the thing you've got to keep organized. Inside is horizontal, outside is vertical. The vertical shifts feel correct. The horizontal ones feel backwards. So horizontal changes are always inside, where vertical changes are always outside. So there's me finally writing it down. Told you I was going to sooner than later. So before we get to what you see reflections, we're going to do some examples with this, of course. So example 2, sketch. And this might be the last thing we get to. We're pretty close on time. F of x equals absolute value of x plus 4, where the plus 4 is in the absolute value. Inside means it's a horizontal change. So this is going to be a left or right change. If that plus 4 had been over here, this would be a vertical change, specifically up 4. But it's not, so it's not. So the plus 4 inside means it's either going to be left or right. And you have to remember that horizontal changes are backwards. Plus 4 is not right 4, it's actually left 4 units. And if you ever don't trust this, you can plug in the coordinate that you get, the bottom of the function on, you can plug it in and see if it matches. So maybe we'll try that out here. I still need more space. So we're taking the absolute value function, which is a v. Here's the ghost image. Again, this was just the basic absolute value, but I'm going to shift it left 4. So I just take the bottom of the v, and I move it left 1, 2, 3, 4 units over here to -4. And then there's that bottom. I can't really draw this too tall. I can't draw past that border, unfortunately. And there we go. There's our function. Now that point right there, that's -4, 0. If you plug in -4 right here, -4 plus 4 is 0, the absolute value of 0, it works. If you had gone right 4, you would have the point 4, 0. If you plug positive 4 in here, 4 plus 4 is 8, the absolute value of 8 is 8. And that point is not 4, 8. It would have, you said it was 4, 0, which would have been wrong. So this is an excellent way of checking if you shifted correctly. Because horizontal shifts are backwards. All right, how about f of x equals x minus 2 in parentheses cubed? We got our the basic function is just the x cubed. This is the basic function, which means it's going to look like that shape, but without ridiculous highlighter width. But it's got a -2 going on inside of it, and the -2 tells us we have a shift. It's inside, so it's a horizontal change. It's either left or right. So it's either left or right 2. Since it's minus and they're reversed, that means it's right 2 units. And again, if you don't trust that, once you graph it, plug in the x value and see if you get the correct thing. So again, here's our ghost image. Here's our basic x cubed graph, but we're going to shift it right 2. Right 1, right 2. So there's that kind of beginning point, the starter point. Up and right from there, down and left from there. Try and make it as best as you can. There we go. So this point right here is 2, 0. And if you plug 2 in here, 2 minus 2 is 0. 0 cubed is 0. It works. If you thought this went left 2, if you plugged in -2, -2 minus 2 is -4, -4 cubed is -64, that would definitely be the wrong y value. And that would say, oh, I shifted the wrong direction, didn't I? So you can find ways to check yourself with this, especially with the weird thing. If you shift these vertically instead of horizontally, that little check would prove it. You say, oh, wait, no, I messed up somewhere along the line. Now, whether you can correct yourself from there, that's up to your skill level. But yeah, it is checkable, believe it or not. All right, we got a couple minutes left. We won't do any more examples, but we will go ahead and lay out the reflection ideas. Here, reflections. So previously we've talked about even and odd functions and how an even function, if you took one side and flipped it left or right, you get the rest of the function. Or an odd function, if you flip it left and down or right and up, whichever is necessary, then you get the rest of the function. So again, that's what we're talking about, taking half of the function and flipping it to get the other half. That's not exactly the same thing as what I'm talking about here. Here, this has nothing to do with being even or odd. Yes, you may get an even or odd function potentially, but it's just saying, all right, if you have a negative outside the core, then it's a vertical reflection. If you have just a negative in front of your x squared, it's outside, not inside, then that reflects vertically across the x-axis. So again, that's using across the x-axis. That's your mirror. Now you might be saying, well, Mr. Beckner, then you don't have a function. No, that's not true, because we're not taking half of it and flipping to get the other half. We're taking an original ghost image and then flipping it so that maybe it points down instead of up. And that would be a function because you then ignored the ghost image. Versus if you have a negative in front of your x inside the core. So again, this first negative is outside, which is why it's a vertical reflection. This negative right here is inside, which is why it's a horizontal reflection. So once again, all horizontal changes are inside, all vertical changes are outside. So what that says is, if you have a negative inside paired with the x, you're going to reflect it across the y-axis. So this is our mirror. So again, the original function might say, look like this. Sorry, that should be a ghost image. But then when you draw it yourself and reflect it, there's your actual image. So you reflected left to right. So when we come back next time on Wednesday, we will continue this by doing examples. You know, I'll give you a retread of this last 90 seconds, but we'll apply it. And the first thing we'll even do is f of x equals negative x cubed. So this is going to be the, ignore this for a second. This will be example 3a. It'll be f of x equals negative x cubed. If you'd like to try that on your own before next class, we're also, I'll spoil it, we're going to be doing f of x equals the square root of negative x. So those are the next two examples with these reflections. So that's it for the day.
All right, so just reminding you of your upcoming due dates. That's going to be it. Like I said, we've got those 2.3 and 2.4 due dates pushed back a little more than normal because of spring break. We will not be having class next week, so if you show up, I won't be here. It'll just be an empty Zoom call. Besides that, have a good one, get some good studying done, get some homework done, and we'll see you in almost 2 weeks. Take care, everybody.